probability for chapter 9. So probability exercise A is sample space and probability. I'm pretty sure in year 9 and year 10 we all learn this. Okay, year 9, year 10 we all learn this. So just go through some definitions with you. What is a trial? A trial is a single experiment, such as toss a coin, throw a dice, run, like have a competition, like something like that. So an outcome is the possible result of an experiment. Okay, outcome is the result of an experiment. So I can say toss a coin, I can have outcome as head or tail. Head or tail. Okay, so the sample space, we use a symbol like that. That will equals to head, comma, tail. So sample space will be a set. Will include all the outcomes inside. Okay, all the outcomes inside. So when you talk about outcome, I will just say head or tail is my outcome. Then the sample space will be put that in a set, list out all the outcomes. An event. Event is a list of favorable outcomes. It is the subset of the sample space. So I can say I have interest in obtaining a head. Okay, I have interest of obtaining heads. I throw the coin for 3 times and I want to observe how many heads I will have. That's my favorable event, or that's called an event. So the event is getting head. Okay, it's an event will be getting head. So event is something I have interest. Okay, something I have interest. The probability of an event A occurring is denoted by probability A. Okay, we say probability A is the probability of getting 3 heads. Okay, so probability A. Some definitions for probability A. Probability A first needs to be greater or equals to 0. Okay, first needs to be greater or equals to 0. You never talk about probabilities like say negative 0.2 or something. And also it needs to be less than 1 as well. Less or equals to 1. You won't say something is 1.2. The probability won't be 1.2. So 100% sure is like something definitely will occur. So the sum of probabilities of all the outcomes in a random experiment must be equals to 1. So the probability of getting head plus the probability of getting tails must give you 1. Okay, probability of getting head plus probability of getting tail must be equals to 1. And equal likely outcomes. And outcomes have same chance to occur. Throw a dice, number 1 to number 6, you have the same chance to get, which is 1/6. But it needs to be a fair dice. Okay, a fair coin or fair dice. If something says a biased dice or biased coin, you won't have probability half-half or 1/6. So it will according to what the question gives you. So any fair coin, fair dice, you will have equal likely outcomes. So in the study of probability, a numerical value based on scale 0 to 1 will use to describe the level of chance. So probability is something happened by chance. Probability of an event in which outcomes are equal likely can be calculated by the following way. The number of outcomes in the event A over the total number of outcomes. So if 2 events have 2 elements in common and together they make up the entire sample space, they are said to be complementary events. The complementary events of any event A is denoted by A dash. We write probability A dash equals to 1 minus probability A. So we have a sample space. And if I said that's probability A, then all the rest, okay, with no intersections, but make entire set. The red part will be A dash. Okay, so except A, all the rest will be A dash. Okay. A card is drawn at random from a pack of 52 cards. Okay, not 5,252. So it's 52 cards. What is the probability that a card is not a heart? Okay, a card is not a heart. So when you have a heart, it will be a quarter of the chance. So not a heart will be 3/4 of the chance. So 1 minus a quarter. So if heart is the event A, then A dash will be not a heart. So 1 minus a quarter will be 3/4. Not an ace. So 1 minus 4/52. You have 4 aces. There are 52 cards in total. That's the probability I can get an ace. But 1 minus that will be the probability I can't get an ace. So that will be 12/13 if you simplify that. That's 1/13. And then 12/13. Example 2, a random experiment may result in outcome A, B, C, D, or E. A, B, C, D are equal likely, and E is twice as likely as A. Twice as likely as A, which is twice as likely as B, C, D as well. So if I use a table to represent the outcome, say if that same area, okay, if all of these boxes are same area. So I have A, B, C, D in each box, and E will obtain 2 boxes. Okay, in total I have 6. The total number of outcomes will be 6 because E is twice as likely as A, B, C, D. So you have 2 boxes there. So the probability of E will be 2 over 6, which is a third. The probability of B dash will be 1 minus 1 on 6, which is 5 over 6. Yeah, which is 5 over 6. Okay, have a look at B. Estimating probabilities. So first is subject probability. So what is subject probability? Okay, remember subject probability not necessary to be true. Subject probability is I have an estimation based on what I think it will be. Okay, that's subject probability. It's not something, it's based on experience. Okay, basis on experience. Well, my experience not necessary to be the true probability. Well, I just like very occasionally observe and risk, and then someone like say Amy just win on that risk, but like very occasionally win on the risk, and I then based on this experience I think Amy will win on the next one as well, and I have a really think there's really high chance Amy can win. I'll say just because of my experience Amy have 90% of the chance can win on this game as well, but this experience not necessary to be reflect the true probability. It can be something occasionally, something not really like very rarely happen. So I say 90% of the chance Amy can win is not an actual probability. It's just a subject probability. It's based on what I think, what I believe. Okay, so basically subject probability is on what I believe, and I give a number. So we just need to know what is it. And the proportion of trials that result in an event is called the relative frequency of an event. So relative frequency of event A is the number of times event A occurs over the total number of trials. So that's based on experiment. It's not based on experience, it's based on the current experiment. I do something, okay, I throw the dice, I throw a coin for 50 times. I want to observe the number of heads I have. I think there will be 0.5 of the chance to get a head. Okay, theoretically I should have 0.5 of the chance to get head. But actually I just have 10 times to get a head. Okay, there are 10 times to get a head. Then the probability of getting head will be 10 over 50, which is only 0.2. Okay, which is something only 0.2. So I throw the coin for, I toss a coin for 50 times. Only 10 times I get a head. I get heads. So the probability of getting head based on this experiment will be 10 out of 50, which is 0.2, which is not necessary to be true for the theoretical probability. But this is called the relative frequency of an event A. And this is also called the experimental probability. Okay, relative frequency will be the same as experimental probability. So based on the experiment, what I will have. Okay, it's calculated the same way as theoretical one. You have the number of favorable outcomes over the total number of trials. Okay, then you may ask me, okay, there's a theoretical probability. There's an experimental probability. What's the relationship between that? Let's say as the experiment we do to throw the coin for 50 times. The theoretical probability will be 0.5, but the experimental probability is only 0.2. They are different. Then why we have two different probabilities? Like which one I should use? Okay, there's something called long run proportion. Okay, there's something called long run proportion. So which means if you do sufficiently large number of trials, okay, you just keep doing this experiment, 10,000 times, a million of times, finally, your experimental probability will be approaching to your theoretical probability. When n is sufficient enough, okay, large enough, let's say 1,000, a million, then your theoretical probability and experimental probability should be approximately the same. Okay, it will be approaching to that. Okay, theoretical probability is long-run probability. Okay, it's long-run experimental probability. Okay, let's have a look at example 1. In order to investigate the probability that a drawing pin lands point up, Katya decides to toss it for 50 times to count the number of favorable outcomes. So what is my favorable outcomes here? What is my favorable outcomes here? Like, what is it? Like, what I want to observe. What I'm trying to observe from this experiment. I just toss the drawing pins. What I want to see. Okay, pin length point up. That's my favorable outcomes. What I have interest to see how many times that can be land up. Okay, so that's my favorable outcomes, which turns out to be 33. So I throw it 50 times, 33 times the pin lands up. Mickey repeats the experiment, but she tossed the same pins for 100 times and counts 62 favorable outcomes. So 62 times is pin up. So 1, what is the Katya's estimate of probability of drawing pins landing point up? Okay, so the probability of like this event, let's call this event A, will equals to 33 over 50. That will give me 0.66. Okay, the probability of event A for, let's say, probability of event A for Katya and event A for Mickey. Okay, AK and AM. 100 times 62 to be land up, so 62 over 100, which is 0.62. Okay, 0.62. Which of these is the preferred estimate of the probability from this experiment? If asked you to choose one from those two, which one you will choose? Do you think the probability will be more approaching to 0.66 or more approaching to 0.62? 62, because the more I do the experiment, the more I'm approaching to the theoretical probability. So the more the better. Basically, the more experiment, the better. So 100 times will be the preferred. So I would say Mickey's estimate. Okay, the preferred one is Mickey's estimate. Number 4. Based on the information available, okay, so all the information available above, what would be the preferred, like a more preferred estimate? Okay, out of these two, the preferred one is 0.62. And based on all the information I have above, what is a more preferred one? Okay, even preferred one. Have a think how many experiments in total I have done. For two people in total, 150. What's the number of favorable outcomes appears in total? 95. Okay, so they separately to do two things, okay, 50 and 100 times. But in total, all the information available, I know in total they make 150 experiments. And favorable outcome will be 95 times. Then an even preferred one will be probability event A, let's say P preferred, equals to 95 over 150. (19 over 13). Okay, the more the better. Just remember, the more the better. So how I can create a more? Okay, I have played 50 times. We have played 100 times. In total, we have played 150 times. That's a more preferred one. Okay, just go through example A and example exercise A and B with you quickly, and let's have a look at exercise C. Exercise C, I'm pretty sure we learned that as well. Okay, multiple stage experiment. The sample space for two-stage experiment can be displayed by a tree diagram or a table. Okay, if the experiment involves more than two stages, a tree diagram should be used. So the table basically only can work for two-stage experiment. But tree diagram can just use to do like more stages. Okay, to do more stages. Okay, example 1, without replacement. Okay, example 1, without replacement. Two letters are be chosen from the word kick without replacement. So if it's without replacement, I won't have the exactly same word. Okay, I won't have the identical word. And for the row and the column, you can name which one is the first, which one is second. Let's just treat the row as the first choice and the column as the second choice. You just need to remember your own order, okay? You can say the column is the first and the row is the second. You just need to remember that and then write the order pairs in the correct order. So we won't have the same letter. So at the same position, we won't have the same K, we won't have the same I, we won't have the same C, we won't have the same K. We still can select two Ks, but it's not the same K. Okay, it's one K at the front, one K at the back. It's not the same identical K. Also, you have K1 and K2. You can have K1 and K2, but you won't have K1 and K1. So if the row is the first, when you write the order pairs, you will write Ki, Ck, and Kk. Have Ki, Ci, and Ki. You have Kc, Ic, and Kc. You have Kk, Ik, C, and K. Okay, the order must be correct. The order must be correct. The element from the row must be the first. Okay, the element from the column must be the second. Okay, so how many outcomes are there in total? Sorry? 12. Okay, 3, 3, 3, 3. You have 4 columns, each column goes 3. You have 12 outcomes. Just count how many things you have right. Okay, the probability of obtaining Kc. Kc, if it's read in the order pairs already, K must be the first one, C must be the second one. How many Kc, like this favorable outcomes you have? How many Kc you have? 2. Okay, we have this Kc and this Kc. We have 2 Kc. Okay? One is here, one is here. Okay, 2 Kc. Therefore, the probability of getting Kc is 2 out of 12, which is 1 on 6. 2 out of 12, which is 1 on 6. Okay, selecting 2 Ks. If you have Kk, you have 1 and 2. Okay, it's 1 on 6 as well. Okay, 1 on 6 as well. Okay, selecting a K and a C. So if it's selecting a K and a C, it can be Kc, it can be Ck. Okay, I just need a K and a C. It doesn't matter with the order. Then Ck, Ck, Kc, Kc. We have 4 outcomes. Okay, we have 4 outcomes. 4 out of 12, which give you 1 out of 3. 1 out of 3. Okay, that's without replacement question. Okay, that's without replacement question. Say if without replacement, I won't have the main diagonal, we won't have any outcomes. Okay, on the main diagonal, we won't have any outcomes. Let's have a look next one. Next one doesn't say with replacement or without replacement. Just say a 6-side die is tossed twice. Oh, no, I mean, it's not, doesn't really say in the main question, like say just below that. Like you won't have a question given you that's a with replacement. That's a hint I give you here. So that's the type of with replacement. That's the type of without replacement. But when you actually get the question, you only say a 6 die is tossed twice. Okay, but like have a think. If you toss a 1 for the first time, will you still have a 1 second time? Is it still possible? It's still possible, right? You still with the replacement. So you need to replace the number back. Okay? So it's a with replacement question. So you will have everything. Okay, you will have everything in the box. So I'm not going to list all of them, but just let me know what is the total number of outcomes. 36. Okay, everything can be filled in because there's with replacement. Everything you can get exactly again. What's the probability of obtaining a 1, 5? How many outcomes of 1, 5 you can have? How many times you can get a 1? Okay, a 1, 5 means you get a 1 for the first time, you get a 5 for the second time. It's only one that case, okay? Only one that case. A 1 and a 5. Okay, 1 first, then by a 5. It's only one case. It's not 5, 1, 1, 5. It's only 1, 5. So there's only one such event, so it's 1 on 36. Okay, what's the probability for double? 6. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 6. 6 out of 36. Give you 1 on 6. Okay, next one. The sum at least 10. At least 10. So we'll count how many outcomes actually will give you 10 above. So 3 plus 6 is only give you 9. It's not enough. You start from 4. 4 and 6 will give you 10. 5, 5, 5, 6, 6, 4, 6, 5, 6, 6. Only those corners can give you some at least 10. You can have a think about that. So 1 plus any number can be 10. 2 plus any number can be 10. 3 plus any number can be 10. 4 only plus 6 can be 10. 5 can plus 5, 6. 6 can be 4, 5, 6. So there are 6 such outcomes. So it's 6 out of 36, which is 1 on 6. Okay, the last one, the sum is not equal to 7. Will you count the sum not equals to 7? What do you count? Sum equals to 7, okay? So that equals to 1 minus probability, sum equals to 7. Well, sum equals to 7. Whose sum equals to 7? Well, I'll still write this cross here. I'll use another color. Let's use the red. So 1 plus 6 give you 7. 2 plus 5. 3 plus 4. 4 plus 3. 5 plus 2. 6 plus 1. Okay, they all give you 7. Okay, there are no more. 1, 2, 3, 4, 5, 6. So it is 1 minus 6 out of 36. That is 5 over 6. Okay, example 3. Find the probability that when a coin is tossed 3 times, one head is observed. One head is observed. Okay, if a coin is tossed 3 times, which means it's an experiment for 3 stages already. Okay, a 3-stage experiment. You can't use the table. You use a tree diagram. If you want to do a tree diagram, okay, I just go for backwards. I know what the tree diagram looks like, but your tree diagram should start from the first one. Okay, you have a head, a tail, the head, tail, and the head, the tail. That's a tree diagram. When is the case you will have one head only. So if you write the outcomes, that will be head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. Okay, so I want to observe one head only. So how many situations, how many events, variable events you can have? One head. How many times you only have one head? Three. 1, 2, 3. Okay, 3 times you only have one head. So how many outcomes in total? 8. So A will be 3 over 8. Okay, I'll say probability head, like say one head equals to 3 over 8. B, at least one head is observed. Okay, what you can do to this one? At least one is observed. You can observe 1 head, 2 head, and 3 head. Which case is not included in this? 0 head. Okay, I have nothing observed. So I can observe, I want 1 head, 2 head, or 3 head. So that will be the probability 1 subtract, I have no head observed. That will be easier to calculate by this way. So that will be 1 probability minus no head. That will give me at least 1 head. So what's the probability of no head? 1 over 8. So it's 1 minus 1 over 8. That is 7 over 8. Okay, next one, I want the second toss result in a head. Okay, which one is second one? How many situations you have second one result in a head? Okay, second one, 1, 2, 3, 4. Okay, 4 times you have the second one is a head. So probability second head. 4 out of 8. D, all head or all tails. So probability will say all heads or tails. How many cases you have all tail or a head? 2. 2 out of 8 is 1 on 4. Okay, for this tree diagram, everything like it's a half. Okay, all the branches you have probability a half. Okay, each one will have probability a half. So let's have a look at the next one. Example 4. Example 4 says box A and box B contains 4 counters each. Okay, A and B have 4 counters each. A contains 2 red and 2 green. B contains 1 red and 3 green. Okay, the probability are not the same for each box. Okay, a box is chosen at random first and then a single counter is selected. So stage 1 is you select one box. Okay, stage 1 will be select one box. It's either box A or box B. Okay, what's the probability I get box A or what's the probability I get box B? Just there's 2 boxes. What's the probability I get this one? Half. Okay, if you already select counter A, you have 2 things can be selected, which is a red counter and a green counter. What's the probability for box A to get a red counter? In A, we have 2 red, 2 green. Half and half. Okay, 2 red, 2 green, the probability will be the same. Same 2 red, same 2 green. Okay, for B, have red or green. What's the probability of getting a red in B? A quarter, yep. And then green will be 3/4. Okay, the probability on each branch will not be the same. Okay, so the outcome will be A, R, A, G, B, R, B, G. But the probability is not a quarter for each of that. It's not a quarter for each of that. That one will be a quarter, that one will be a quarter, that one will be 1 on 8, that one will be 3 on 8. The probability is a little bit different. The probability is different. What is the probability of selecting box B and select a red counter? So basically, I want the probability of that. I want the probability of B, R. Okay, I want box B and I want the red counter. One on 8. Okay, what's the probability of selecting a red counter? Okay, I don't mind which box I get a red counter. I just want a red counter. So that can be the probability of A had a red counter plus the probability B get a red counter. Okay, from A get a red counter or from B get a red counter, they all can be satisfied. So A get a red counter will be a quarter. B get a red counter will be 1 on 8. 3/8. Okay, example 5. There are 5 people participating in an event. 2 awards will be given to 2 people randomly. Can't given to the 2 awards to the same person. What is the probability that person A will win one of the awards? Okay, this question is a little bit tricky. It seems quite easy, but you can choose your own method to do it. You can choose your own method to do it. You can use a tree diagram, or you can use table, or you can just purely on thinking. Okay, so basically I have 5 people here. Okay, I just randomly throw a word to someone. Okay, just go into back and I throw a word to someone. someone get it and going out. Okay, it's not involved in this one anymore. Then there are 4 people here, and I will throw this again, and another one will get the second award. Okay, so I want to say, what's the probability that a particular person will get one of the awards? It can be either prize 1 or prize 2. Okay, one or award 2. Let's say probability A can win an award will equals to the probability A win the first plus the probability A win the second. Okay, A win 2 awards. You can win one of that. Can be you win the first one plus you win the second one. There's no intersections between win the first one and the second one because you can't win both. Okay, so it's either win the first one or win the second one. Let's have a think. What's the probability you will win the first one? Well, there are 2 awards. As I said, there are 5 people here. What's the probability you can get the first awards? Now just like throw something to 5 people. Like what's the probability 1 people can get it? 1/5. Like it's really random. 1/5. Okay, that is already the case that you can win the first awards because you don't really mind who wins the second. Okay, doesn't matter. It's not my business. Okay, I win 1, I walk out. There's just 4 people left. And then I just throw another one, but I don't care. I don't care what's the result. I already successed. I win the first awards and walk out. So just 1/5. The probability I can win the first awards is 1/5. Plus the probability of winning the second. Okay, probability winning the second means probability not win the first. Intersects win the second. Right? If you want to win the second awards, it must mean that you are not winning the first. Okay? You can't win the first. You remain in the same room, and then I throw another one. You win the second. So not win the first intersects with you win the second. That must happen at the same time. So what's the probability that I can't win the first one? 4/5. Yeah, 4/5. Intersection is times because this event doesn't finish. And I want to win the second. What's the probability I can win the second? That's the important thing. 1/4. Because 5 people, someone win and someone walk out. And I have 4 left and I'm involved. And the probability I can get it is 1/4. So I will have 2/5. Okay, that's how you do it. That's how you do it. Or you can draw a table. Okay, so this table means the row will be the person receive first award. And then these are the person receive the second award. Okay, the row, it doesn't matter which one you have. Okay, just the row represent you receive the first, column receive the second. Because same person can't receive both. So these must be cross. Because that's a without replacement case. You can't receive both. You can't have AA, BB, CC, DD, EE. So that will be cross. And then how many, I'm not going to write it down. How many outcomes are there? Yeah, total outcomes is 20. Okay, you have 5 columns. Each column you have 4. Okay, 4 times 5 is 20. And what is the case? A will win any award. Okay, this one A will win the second award. This one A will win the first award. There are 8 events. A will win an award. Okay, 8 events. A will win an award. So probability A win will be 8 out of 20, which is 2 on 5. Okay, which is 2 on 5. Okay, we just stop here today. We have another 3 pages to go before the exam.